All right, I'm here to talk to you today about the units of measure that we use in radiography, in this case specific to electromagnetic radiation in the system of SI units, so the system international units of measure. Here we go. Electrical energy. We measure electrical energy for our purposes in the joule. The joule is the amount of energy required to move 1 amp, about 6 times 10 to the 18th electrons, through 1 ohm of resistance for 1 second. The definition of a second: 9,192,631,770 oscillations of cesium-133. That's how long, that's how many oscillations of this element called cesium happens in over 1 second. It's a very reliable, essentially a very reliable clock. Anyways, the joule. In kinetic terminology, it's the amount of force transferred to an object when 1 Newton of force acts on it over 1 meter of distance. So what is force? Force is, simply put, any action that changes the motion of an object. Isaac Newton says, all objects will remain in a constant motion unless acted on by an outside force. You can think about this like the Earth orbiting around the sun. In the sun's gravitational field, the Earth takes the path of least resistance and continues on that trajectory unless something else happens. Unless, for example, we are bumped into or the gravitational field changes. In any case, force is anything that changes the motion of an object. The Newton's the unit of force, the amount of force required to accelerate a 1 kilogram object to a rate of 1 meter per second squared. Okay, so let's talk about some bases for our units of measure, the base units. First off, this is based on the metric system, based on units of 10, probably because we had 10 fingers. Still have 10 fingers. Length, a unit of length. It's now standardized as the distance light travels in a vacuum in 299,700. Okay, so our base units of measure. Starting off, we should understand that this is all based on the metric system, which uses units of 10, powers of 10, orders of magnitude increasing by powers of 10, however you want to word it. And the reason for this system being based on units of 10 is probably because we have 10 fingers. Not that it's easier to calculate with. Other base units are actually easier to calculate with, but in any case, units of 10. Length is standardized as the distance light travels in a vacuum in a short period of time. 1/299,792,458th of a second. That time is measured by a cesium-133 atomic clock, which emits pulses of radiation at very rapid and very regular intervals. This was decided on in 1984 at the Geneva Conference on Weights and Measures. So our unit is the meter. Again, that's that distance light travels over 1 second, or one period of a second is 1 meter of length, and it's a very reliable way to measure that distance. For our purposes, we use smaller units more commonly, unless we're talking about like a radio wave, for example, then we'd be using kilometers. But for our purposes, we're using small units. X-rays have very small wavelengths measured in nanometers, for example. Atoms are very small, measured in angstroms. So let's learn these units. The centimeter. This is 1/100th of a meter, or 10 to the negative 2 meters. The micron, 1/1,000,000th of a meter, 10 to the negative 6 meters. The nanometer, 10 to the negative 9 meters, 1/1,000,000th. And the angstrom, it is 1/10,000,000th of a meter. The angstrom is the unit that refers to the width of an atom at its outermost shell, the angstrom. Time. Time is measured in seconds. The second is the base unit of time in the SI system of units. It's equal to the duration of, get ready for it, 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of cesium-133. Basically, this means this atom and other atoms, but specifically this atom, oscillates between a high and low energy state a specific number of times in 1 second, and it will always do this. And every atom of cesium-133 will always oscillate this exact same number of times, so we can reliably build a clock using cesium, because a clock is anything that just repeats the same action over and over again, and cesium repeats the same action extremely reliably. So when you hear about the atomic clocks in Colorado, for example, they're using cesium as their element in the atomic clock to keep time. Most commonly, we just use the second or millisecond. Millisecond would be 10 to the negative 3 seconds. Think milliseconds like when we talk about making exposures for our patients. Okay, next up is work. We talk about work as the moving of an object. So work is just force over distance, or said more correctly, force in newtons multiplied by distance. And energy is the ability to do that work. There's all different types of energy. I've kind of put together a few that are important to us, but know that there are more types of energy than this. Potential energy, the energy of position. Nuclear energy, the energy within the nucleus of an atom. Mechanical energy is the energy of me moving something. That's more of a macroscopic idea. Gravitational energy, the energy of being within a gravitational field. Electromagnetic energy, we're going to talk about that more in a moment. And kinetic energy, which in pure terms is just the energy of motion. All right, there's energy. Energy has the ability to do work, which is to move an object. And then there are objects. A better word for an object would be matter. Matter is the stuff of the universe. This is the things that have mass and occupy space. We measure matter in units of grams. Gram is a unit of mass. It is equivalent to a cubic centimeter of carbon. Think pencil shavings. Take a cubic centimeter box and fill it up with pencil shavings, pack it full of pencil shavings. That box has a mass now of about 1 gram. The kilogram, we use the kilogram a little more commonly, especially when we talk about like absorbed dose in exposure in coulombs per kilogram, or absorbed dose in joules of energy deposited per kilogram of tissue. A kilogram is 1,000 grams, equivalent in standard units to 2.2 pounds. Okay, the thing I've been trying to get to, electromagnetic energy. This is one of several types of energy. The important thing to remember starting here is that although there are several types of energy, energy is never lost. It's never created from nothing. Put a little asterisk there, but essentially it's never created from nothing, and it has to be able to change forms. That means there has to be some conservation of energy from one interaction to the next. Energy is conserved from one interaction to the next, or throughout an interaction, energy is conserved. All right, so starting off, radiation. Radiation, I don't mean radiation in terms of like ionizing radiation or any specific type of radiation. Radiation is just energy in the form of waves or particles moving through space. So radiant energy always has a kinetic property to it, and then it's always some energy of motion. Our type that we're going to care about here is electromagnetic energy, or said more correctly, electromagnetic radiation. Electromagnetic radiation originates from the electron. The electron is a negatively charged particle with an atomic mass of about 1/1800th of a proton. And it's the origin of electromagnetic radiation. So electromagnetic radiation is a dual wave in the electric and magnetic field. So the electric and magnetic fields are disturbed, kind of like water in a pond is disturbed when you you drop a pebble into it. These types of waves, though, have no mass, no charge, and their velocity is fixed. The velocity is the speed of light because it is light. The velocity is equal to c, the constant, the speed of light, which is equal to 3 times 10 to the 8th meters per second, or said in another way, 300 million meters per second. So when an electron changes, as in our case, loses potential energy or kinetic energy, it emits a photon, a single photon of electromagnetic radiation. The energy in that photon is equivalent to the loss of kinetic or potential energy. I put loss in quotations because it's important to remember energy is conserved. The energy that was lost from the kinetic or potential is just converted into the energy of the electromagnetic wave, the photon of light traveling away from the electron. So I've shown to the right here the image where you see an electron, and its electric field lines are pointing toward it. That's what we mean by negative electric charge. A positive electric charge would be the opposite. The electric field lines would point away from the object, from the particle. But we're talking about an electron. Its electric charge points right toward it. When that electron changes its position or its momentum, the electric and magnetic fields are disturbed. Think dropping a pebble into a pond. That disturbance creates a wave of electromagnetism that radiates away from the electron at the speed of light. Electromagnetic waves are measured in units of electron volts. All waves share the same properties. Our electromagnetic waves have some special properties to them, but let's start with what are wave properties to begin with. Amplitude, wavelength, velocity, and frequency. Amplitude is the height of the wave. Not so important for radiography because all of our amplitudes are the same. Wavelength is the distance from crest to crest of a wave, measured in units of meters, small units like nanometers or angstroms. And velocity is the same for all electromagnetic waves. It's that speed of light, 3 times 10 to the 8th meters per second. And then frequency. Frequency is the number of wave cycles per second, so measured from a given point. So you pick a point in space, the number of waves that pass that point per second, that's the frequency. 1 hertz is defined as 1 cycle per second. The wave formula. Wave formula is pretty straightforward, and we actually don't, for radiography purposes, don't even need to really know much about calculating it. I think what's most important here, what you should take away from this video, are the relationships between frequency and wavelength. So the wave formula is velocity is equal to frequency times wavelength. If velocity was a variable, then we would need to know velocity each time. But velocity is not variable. For electromagnetic radiation, velocity equals c, as in the speed of light. So for our purposes, c, the speed of light, is equal to frequency times wavelengths. The important thing to remember here is since v equals c, we only need to know the hertz or the lambda wavelength. We know one, then that will tell us the other. And even more important than that is the relationship. The relationship between frequency and wavelength is inverse and proportional. That is to say, as wavelength decreases, frequency increases, and vice versa. Okay, that then brings me to the electromagnetic spectrum. It's important to remember that all photon emissions are discrete, as in one electron loses potential or kinetic energy, position or momentum, and that one electron emits one photon of electromagnetism. Remember, they all travel at the same speed, so it can't be velocity that changes their energies. It has to be wavelength that changes their energies. Low energy waves have long wavelengths. For radio waves, that wavelength is approximately 10 to the 3 meters. That's roughly in the kilometers of length. We're nearing wavelengths that are almost miles long. Higher energies, the higher energy, the shorter the wavelength, as in X-rays, happening at around 10 to the negative 10 meters. That, again, if you were paying attention from earlier, that's about 1 angstrom in length, 10 to the negative 10 meters. So this electromagnetic spectrum pretty clearly lays out the difference from low energy on the left to high energy on the right. And it's all to do with frequency and wavelength. Again, if you know frequency, that will tell you wavelength. And high frequency equals short wavelength. Low frequency equals long wavelength. And long wavelengths equal low frequency, and all the other associations that you can make as well. It's important to remember the relationship between wavelength and frequency is inverse and proportional. Okay, the wave-particle duality. This is just sort of an extra thing to tack on to this here. For radiography purposes, we pretty much just treat X-ray photons as if they're little packets of light that have almost no wave properties at all. You'll read about wave-particle dualities, and people will make arguments for this dual nature. And again, it's often said that electromagnetism has this dual nature. Here's the real deal, though. Waves are waves, and particles are particles. How can one thing be both? The answer? It isn't both. Electromagnetic waves are always waves that in some cases behave like particles, have particle-like properties. The particle behavior comes out, the particle behavior of waves comes out in this. All emissions, and for our cases, actually, all emissions and absorptions happen discretely. One X-ray photon absorbs into one electron. One electron emits one X-ray photon. The action is always discrete. Even for radio waves, it's always a discrete, one at a time action. That's one particle aspect of the wave-particle duality. The second particle aspect is the one that we really think more commonly of. It's at sufficiently short wavelengths, like X and gamma rays. The waves are so close together that the waves begin to behave like particles, as if the waves are all in one spot at the same time, kind of like a particle. A particle is all in one spot at one time. When the waves get close together, they sort of act like that. At long wavelengths like TV and radio, though, the wave nature is clearly evidenced. It's a wave. They're always waves. At short wavelengths, they behave somewhat like particles. And it is always important to remember that the emissions happen one at a time, as in quantized, from the word given in the word quantum physics or quantum mechanics. Quantized one at a time. They are emitted or absorbed one at a time, discretely, and they travel through space as waves. That's where the wave-particle duality comes from, but always go back to they are always waves. Waves are waves, particles are particles. All right, and thank you for watching my video on the units of measure and electromagnetism.